Now, a lot of the work we do and problems we solve in this course is going to deal with showing that two triangles are congruent. Um, Now, if they are congruent, the definition of congruence is that two triangles are equal in all respects. That all their sides are exactly the same, their angles are exactly the same. So, in two different triangles. So, we have four different ways we can prove this. And we've got to be able to quote these proofs. We've got to be able to prove three things in each of them and then be able to state, well, why. So, and we say proofs, but we can't formally prove, but we should call them an axiom or an assumption. Proof will be used a lot of times. So the four ways we have: all three sides in one triangle are equal to the other three sides in the other triangle. So what we call a side proof. So all three in one are equal to all three in the other. Two sides in one triangle are equal to two sides of the other, and the angles contained by the angles of those two sides. What we call the included angle. So you have to have the two sides. Once you've got two sides, you have to have the angle between them to be proved. So we have two sides and one of the angles over here, not good enough for a congruence proof. So it's got to always be the angle between it. So keep that in mind when you're looking for the proof here. Two angles and a corresponding side. So once we've got two angles in a triangle equal, really we've got three, and that forms a proof. That forms the basis of a similarity proof. But that's why we only say two angles. But once we've got two angles, all three, so they're similar. But to get exact, we have to have a corresponding side. So we have to look carefully at the side opposite a particular angle to make sure that's the same in both triangles. But that's what we call an angle side. And we have one where we have a right angled triangle. So we get a right angled triangle. What we're looking for is the hypotenuse to be the same, and then one of the smaller sides to be the same. So as soon as we've got a right angled triangle, if we've got the hypotenuse and the shorter side to be the same, then we have when we have congruent triangles. So there's our four proofs. So how do we see them? Well, in this figure, we've got ABCD with AC down there. We're told that AC bisects BAD. So we're told that these two angles are equal, and we're also told that AB and AD are equal as well. So, well, let's see if we can prove that prove that AC bisects BCD. Well, we need to prove congruence first. So, AC is a common side between these two triangles. AB and AD are given, and that's all we need to write. It's just given as in the question, so there's nothing to prove. And we're told that BAD is bisected by AC, which means that BAC and DAC would be equal. Well, there's two sides and the included angle are equal, so these two triangles are congruent because of side angle side. Now we must include the reason there. So that means if those two angles are equal, those two angles are equal, and also these two angles must be equal as well, which means that these two sides, because they're congruent, they're equal because they're corresponding angles in congruent triangles, and we must include that reasoning as well, which means that AC must then bisect BCD, and there's our proof. In this triangle here, ABC, we're told it's isosceles, and where AB is equal to AC, DE and AC are equal. Show that ADE is isosceles. Well, if that's the case, our ABC is isosceles, so ABC and ACB are equal. So those two angles are equal. And then we get corresponding angles here from both of those. And therefore, we have two angles equal in the triangle, so the sides opposite must be equal as well. So ADE is isosceles. So show that DB equals EC. So we know that AB and AC are equal, and AD and then AE must be equal. So if we take equal sides away from other equal sides, so equal parts or an equal interval subtracted from equal sides, what's remainder must be equal, and that's what all that is saying. So we've taken AD and AE, which are equal, away from AB and AC, which means that DB and EC must be equal as well. And then show that DBC and ECB are congruent. Well, if we look there, that could be a common side of both triangles, because we've got the triangle here and then the triangle there, and they're the same. We also just proved from in the last part that these two sides were equal, and we also know that we've got the base angles of an isosceles triangle being equal, so we've got two sides and an included angle, so side angle side works for us. We've got a parallelogram, proved that ABD and CBD are congruent, and then proves that AD is equal to BC. So what do we know? Well, we know that the opposite angles in a parallelogram are equal. So DAB and DCB are equal. DB is a common side, so we've got that. And we also know we've got alternate angles. So ADB and DBC are equal. So we've got two angles, which means all three angles are equal, and we've got a common side. That means, and which are opposite the same angle, so they must be congruent because they are angle, 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 and which then we can say, well, therefore, those two sides must be equal because they're corresponding sides in congruent triangles. In this one, we've got ABCDs are square, and lines are drawn from C to M and N, and they're midpoints. So what we need to do first is draw a diagonal AC. And we know that if we draw a diagonal, those two would be, that must be bisect. They both become 45 degrees. So we know MAC and NAC would be equal. So those two, so there's an angle. We know that AM and AN must be equal as well because these 2 points bisect a square, and we know the square is equal, sides are equal, so they must be equal as well when they bisect it. And then we've got AC is common, and therefore we have two sides and the included angle, which means we must have congruence of those two. And therefore we can say that MC and NC must be equal because their corresponding sides are congruent triangles. They like putting that type of question in as a last part of a problem. Nice little mark. And that's all we need to really say. It's like, oh, well, I've just proved congruence. Two sides there, they're in the congruent triangles, they must be the same. So there we go. That's how we do some congruence proofs. As I said, you're going to see a lot of those ones. A lot of the questions you're going to face deal with proving congruence. Sometimes they're easier, sometimes they're harder. You've just got to make sure you get all the data that you need. And every time, you're looking for 3 pieces of information.